In the previous lecture, I explained some of the ideas of sparse distributed memory, and in this lecture, I will explain all the ideas. Because these ideas are very important for if you want to understand the articles of DeepMind, such as neural Turing machine, such as neural differentiable computers, and many other articles that are based on this idea of sparse distributed memory in 1988 by Kanerva. There are many good articles and for example, this one is really beautiful. It's the extension and development of the article of a differentiable neural computer because they use multiple blocks of memory instead of just one block of memory. And these are very important. Sparse neural networks are a very important class of neural networks. Also, spiking neural networks is very important. So there is a difference between conventional RAM and sparse distributed memory. One significant difference between the SDM and conventional computer memory is that SDM has a built-in ability to generalize. But you know your RAM does not generalize. So this means that when an association X and Y is stored, then for inputs which are similar enough to X, the SDM will produce output which are the same as Y. For example, for auto-associative memory, when I say a noisy version of 1, when I give it to that, it gives me 1. So it's input-output. This is we call it auto-associative memory. But when I hear the word, for example, NLP, my mind associates it with Professor Christopher Manning in Stanford. And then it associates with something else. And then it associates with lots of things. And so this is how your brain works. Lots of associations. It's like a jungle of associations, and it creates, and all of the dynamical systems in your brain is a dynamical system. Sometimes it gets closer to a limit cycle. Sometimes it gets closer to a fixed point, stable fixed points, and it's a complicated. That's why it's a complex systems. And they work it in Max Planck under the framework of complex systems. So SDM overcomes the above problem by distributing each stored input over many locations and retrieving from a distributed set of locations. So we just get all locations instead of just naively getting the closest one. That's why we call it distributed. For example, the input 139 is here. 139 is also between these and the lower and upper bound. 139 is also between that. 139 is also between these. So these are activated. These neurons are activated. So it's not just one read, it's a couple of reads. And we use, I will explain. So a couple of them are activated. Whenever we give an input, a couple of them, because it's intersection of many of them, a couple of them are activated. And so your input that is coming here, your input and output is going out, your input is written into each of these locations. And I will show you how. Because Whenever input is written, for example, assume that these nodes are activated, and then for any one, you increment, the counter is incremented. For example, 3, 4, 5, 6, 7. And for any 0, it is decremented. For example, if it is -2, it becomes -3. This is how the counter works. And the counter has a biological implementation, delta Wij, with the Hebbian law, that is the most important part of biological neural network, is like beta psi I psi j. So if psi I psi j, if they are activated, these neurons, there is a coefficient. So the amount that the weight is increased is like this. So the amount is because sometimes the weight could be minus, sometimes it's positive. Sometimes your neurons are sometimes excitatory, sometimes inhibitory. So they have a biological equivalence, no problem. The process of writing or storing a vector into the memory consists of the following steps. First, we draw an n-dimensional Hamming distance around the addresses of the input vector. In the plane, this can be visualized drawing a circle. For example, circle, the distance between them is d. So all neurons inside this circle are activated. All of them, you should see the counter of them, and then you add the counters, you add the value of these counters, and yet you give it to a threshold to make sure it's less than 1, and then what is the output is just 1, 0, a bunch of 1 and 0, so that is the output. But one important thing about this machine is that what you give in, it gives out, but this one it could be recurrent. So it becomes a dynamical system. That's why Canerva shows these figures like this. You go to another location, then you go to another content, then you go to another content, and sometimes these trajectories could be chaotic. Sometimes it converges to a limit cycle. Sometimes it converges to a fixed point. Sometimes it is distracted from an unstable fixed point. So anything that you know from nonlinear dynamical systems could happen. And for retrieval mechanism, we say that the contents of the buckets of all selected locations are summed arithmetically, and then the sum is thresholded, because at the end of the day, you just need 0 and 1, and not the value of a counter, such as 7, 8, 9. We don't need them. We just need some values that can be interpretable. So that can be, because what you give to the system is a bunch of 0 and 1, and what you expect to be out of the system is also a bunch of 0 and 1. So as I said, for example, it selects a couple of rows. This is like differentiable computer or neural Turing machine as well, because you have a matrix of m rows and, for example, n columns. For example, you have m number of points in your RAM, m blocks, and n is just the vector for each, for example, the content of that. So here they're activated when we query something. We know the address of that, and then we query that, and we take with the Hamming distance of d, for example, we take all of the neurons. It means that we take all of these rows that have a Hamming distance less than d, and now for each of them, if the input is 1, it means that the counter should be incremented. For example, 1 becomes 2. And if the input is 0, it means the counter should be decremented. So if it is -1, it should become -2. And so, for example, these are the values of the counters for different addresses here that are activated, like the nodes inside here. And then you sum them, because this is the summation. You sum them -400 plus 77, and if you give it to a threshold, 77 is just 1, -400 is just 0. So the output is just a bunch of 0 and 1. So if your task is auto-associative, your input could be a noisy version of 1. The output is just the denoised version. But in your brain, it's not just auto-associative. It is also hetero-associative. So maybe the input is, for example, NLP, natural language processing. Your output could be Stanford NLP group, which is really amazing. So your mind associates these two words together. So this is how we draw inspiration from this system to use it. So this is how DeepMind company used neural Turing machine, and also neural differentiable computer, and many other ideas are based on this beautiful idea that is inherent in your brain. That even now that you are thinking about it, your brain is doing this, is implementing this. And so you know what is the radius. So you know that this is a summation of all of these blocks that are selected, because each of them is like a counter. This is the summation, but we need a threshold sum like here to give a bunch of 0 and 1. This is how you retrieve something. And when the reconstruction is similar to the remembered input, we talk about auto-associative memory. For example, the original one is here, but the reconstruction is here. You degrade it, for example, you have a noisy version of that, then becomes this. So as I said, you can think about this Z. What is this Z? Look at here. This Z is the output. Is the output of your system. Your output could be the input of the next step. For example, let me tell you, DeepMind implemented differentiable neural computers, and they have a controller like an SDM. You have a set of inputs, and here is a memory. Here, so the controller says what are the, they call it key variable. It gives some of the variables that should be known for updating the memory, because M is M plus something. And then, so what is output, and red could be feeding to the system again. This is like this. Z becomes Z1, then Z1 becomes the next input, it outputs Z2, then Z2 becomes the next Z3. So it's a dynamical system. In dynamical systems, sometimes it converges to a fixed point, sometimes it diverges. For example, if it's here, it's on a stable point here. Whatever point is here, it goes out. Sometimes it goes to a limit cycle. It converges to a limit cycle like this, converges to this circle. For example, it goes around of the, so it's a limit cycle. Sometimes it's, so many different phenomena. But because a dynamical system has many fixed points, assume it is hyperbolic, there is no center manifold, then if a perturbation around this fixed point could lead to a different fixed point, and then a different noise would drive it to a different, to go around a different neighbors of a different fixed point, and then around this, and sometimes it becomes chaotic, and even in this simple hyperbolic system. And they're auto-associative, as I said, so you don't know it associates, it's like completion of a pattern. But sometimes it is heteroassociative. For example, the type of the input that you give it is different from the type of the input, and there are two different volts, like bidirectional associative memory, which I've explained in my playlist for Hopfield network. Hopfield networks has a limited capacity, but now we are going to the world that has lots of capacity, and your brain it has infinite capacity, but many people argue that it has finite capacity. I can prove that it has infinite capacity. So because if you remove your assumptions, you will see that your brain has an infinite capacity. And it's like a very interesting system. So there is a difference between auto-associative memory and heteroassociative memory. Auto-associative retrieves a previously stored pattern. Heteroassociative is different from the input, is different from the output, even different format. So this type is similar to this type, it's auto-association, but the nature of Niagara, this word, is different from the nature of the other concept. So SDM can be used also as a heteroassociative mode. In this mode, the contents portion of an input vector is not generally equal to the address portion. In general, the two do not have to be the same dimension either. However, when they do have the same dimensionality, SDM lends itself to storing and recalling of sequences. Consider a sequence of n-dimensional pattern vectors, P1, P of 2, P of 3. They are pattern vectors. Examples of such sequences might be, for example, a sequence of motor control parameters for controlling the trajectory of a robotic arm, a sequence of musical notes, or any other things that you know. So a sequence can be stored by using an element P of I as the address, and the element that follows it, Pi plus 1, as the contents of that. You can define different complex systems by drawing inspiration from these things. So using a queue, this is just one of your queues. Using a queue close to any member of a stored sequence iteratively recovers a sequence that converges. So it's very similar to the idea of Hopfield network. You have a bunch of valleys, and depending on your initial condition, it may converge to different patterns that is stored in your brain. But Hopfield network is limited. It's 0.14 number of neurons, so the number of patterns is limited by this one. This is the upper bound. But you see that this sparse distributed memory is much more general. The number of, a dynamical system can have different trajectories, and any trajectory could be a different thinking process in your brain.